Hey, should I get started? Good. All right. Yeah, thank you for the invitation. Thank you for the very nice introduction here. I hope this voice is okay for people in the back.
Okay, let's check to see if people can hear you online.
As well, yeah.
Yes, we get it.
I think our microphone is up here. So if you just kind of speak outwards to us, then I think we'll hear you.
Okay.
Oh, I'm sorry. The microphone is on the wall. So if people, we'll try to adjust it.
Okay, sounds good. I'll speak to this. Yeah,
I think as long as you speak loudly to us.
yeah, for sure. Yeah, it's very nice to be here. So having some of the folks here already. That's all of my demographer friends have their trajectory traced back to this department in some way. So it's really nice to finally be here and get to meet all of you. So yeah, it's very nice to be here. So the topic I'm going to talk about today, I think I wrote down this title a while ago, and without realizing how ambitious this whole sentence is, but I'm going to try to pass through some of the things that I think about the students working with me and some of the other collaborators collectively thinking about in terms of analyzing essentially verbal autopsy data. Okay. All right. Yeah. Sure. Maybe click on screen. Oh, yeah, there we go. Thank you. I feel like I should probably start with a little bit of background, just in case for people who are not very familiar with what verbal autopsy is, what are we talking about here. So this is probably not a big surprise to people in this room. That's for a large part of the world, the civil registration vital statistics system is really lacking, and especially for people living in the low and middle income countries, as you can see on the map, there is really a very low coverage of the civil registration system for much part of the world. The particular thing that we're dealing with here, essentially, as you can infer from the word autopsy here, is about the cause of death, and particularly for cause of death, high quality data is estimated to be lacking for essentially 2/3 of the world population. And in most of the places where you really need to know about cause of death, those are places you have the least amount of data.
Has China changed dramatically since this picture, or is it still from what
So I think it's better than this, but I think there are more sample registration systems. But if we're talking about the civil registration system as a whole, it's still not. That's my shallow understanding of the broader picture. Yeah, and by the way, I should say that probably at the beginning, but feel free to interrupt me for any questions. I'm happy to answer them as I go along. Okay. So as I was saying, that's the thing that we're essentially trying to estimate here is about cause of death. And needless to say, that knowing cause of death information is really fundamental to any kind of system. Because if you only have cause of death information for a part of your population, a small subset of your population, with this partial picture, it's really difficult to prioritize, allocate resources, or evaluate any of the public health interventions. So just as some of examples, so this is a project we partner with a few study sites in Africa. We're using verbal autopsy to essentially look at the cause of death distribution, especially focusing on HIV before, during, and after the rollout of the ART in some of those study sites. So these kind of things are essentially what we want to get at. We want to understand about the population. And again, this is something that if you only have information from medical facilities, you only know about people who die inside the hospitals, you wouldn't get this complete picture of the entire population. Okay, so this is kind of the end goal. That's where a lot of our method development is trying to achieve at the end. All right, so with that, probably should define what verbal autopsy is. So essentially, the picture you're seeing here are people conducting verbal autopsy in the fields. The concept was first proposed for a while ago, first as a study project, And the idea is basically that we're going to collect information about cause of death by going to the places where the deaths happen and interview the people who are familiar about the deaths. So typically that's their relatives or caregivers, and we're going to ask a lot of questions about what happens before the death. Okay, so this is typically for people for deaths that happen outside of hospital where you have no information about their cause of death. There's no medical certification anyway. Right. And just to give you a sense of what the questionnaire will look like, it goes through a long, very long list of indicators. So the interviewer will ask questions, for example, whether or not there was fever. If yes, a bunch of fever-related questions. If no, you move on and talk about and ask about other indicators, whether cough, or there something else, were there a traffic accident involved, etc. Okay, and this list goes as I said, it's a very long survey. Typically, it goes through a few hundreds questions at the end of the day. All right, so that's a kind of the setup of the verbal autopsy, and a few things happened in the last decade or so. So the two things I want to highlight here, that's one is that increasingly the verbal autopsy data are analyzed by computers, by software algorithms. So at the beginning of the idea of collecting verbal autopsy data is that we'll ask physicians to review the records and we'll assign the cost. But as you can imagine, that's really time consuming. It's really hard to scale up. So more and more people are coming up with software, and our group actually worked a lot on that direction. So this is actually a plug for a recent paper that just came out on the R journal, and we have a website where we put together a lot of the software we've been developing, or we're collectively known as the OpenVA team. We're hoping to make this more of a transparent and open source endeavor in this realm.
We have a question on the chat. Somebody's asked, Robert Chung is asking, how long after the death are the verbal autopsies collected?
That's a very good question. So there's a lot of debate in the field about that. Should probably look at that. Anyway, yeah. So typically there is a set of grief periods that you wait until the period is over, and then you send an interviewer to the place. But the specific setup of how long you wait depends on the context. Different countries have limits. Yeah, ranges from a few weeks to a few months, but not immediately after death.
And could you talk a little bit about the kind of frame? Is the idea that an area would say, okay, we're going to do verbal autopsies, and then we're going to take a sample of deaths, or is that what's coming up? Or?
Yeah, very good question, because that's on the next slide.
Okay.
Yeah, so initially, as I was saying, that this is more of a research project. You have study sites where you monitor the area around the study sites. But increasingly, what happens is that there are country-level effort where people want to incorporate verbal autopsy into their CRVS system. Then it becomes much larger scale, where you have a death occur, as the flowchart here shows that the notification goes to some civil register, and it gets notified, and after a waiting period, the health worker will be sent to the village or to the place of death, the community, and they will conduct verbal autopsy, process centrally, and so potentially using some of the softwares or statisticians at this step, and then essentially all of those gets to be stored in the vital statistics system. Right. So yeah. So I guess the point here is that it's more and more increasingly people realize the need of collecting from the cause of death information for that part of the population. And there's the push to essentially make this more systematic effort instead of just a particular grant projects where they monitor specific small area. Does that answer that? So basically all of the deaths are supposed to have a verbal autopsy, and all of the deaths are supposed to be analyzed and saved.
But the setup is not that a country would try to get 100% death reporting and then do a sample where we're going to sample 1% of those and get the autopsy. That's not the
right.
way.
Usually that's not the way. But there could be validation studies where people sample subsets and then they try to get the cost from a different mechanism and try to compare different methods. But the idea is essentially is that we're going to have a system which we centrally process all of the information we collect from DA. Okay. It's good.
I have a question.
Yeah.
So when the death occurs, this looks like, so a death can occur in a hospital or it can occur at home.
Mm-hmm.
So do you have a sense of, the deaths that occur at home, is there a health worker who's reporting it to the registrar?
Yeah, so I think the deaths occur here mostly correspond to deaths occur at home. Just because in hospital there's certified cause death procedure. The exact mechanism of how that happens, I think it depends on the context, but I'm not super familiar with exact notification mechanism.
Just one more question on the time lag. Are there any studies that try to get at the quality of data the farther out you go from the death? And is there even a sense that you could ask a year later or 2 years later and still, get pretty good information? I'm just curious, like how immediate it needs. I know you don't want to do it the next day, but how close to the death does it have to be to get reliable data?
I would very much like to have this kind of study, but at least I haven't seen, because one of the things we're going to get at it is eventually is that it is hard to conduct the validation study for the target. So even if you can imagine a study setup, what do you evaluate at the end of the day? How do we know which one is better? Can be a tricky thing. So I think the field collectively don't have a good answer of how to do the right validation at the end.
I see. I wonder if you went 3 months later and then again 12 months later, even just the reliability there, just the correlation between those two would give us some notion of how noisy the reporting is. We wouldn't necessarily know the truth, but statistically.
Yeah, there are a lot of related similar studies, like maybe not even specifically about the timing, but there is also the considerations like you want the interviewer to go in person, do you want to do a telephone interview, do you want to do a telephone interview and then a follow-up? So there are a lot of choices people can evaluate, but again, at the end of the day, is how do we evaluate once we collect 2 arms of data? That's still not very clear at this point, I think. Great. That's thanks for all the nice questions. Thank you. So if no more, I'll move on a little bit here. Okay. So I said promising this ambitious title, I'm gonna address some of the gaps in the VA research. And I think as our discussion is already leading us to this idea that's I think a lot of the VA studies nowadays is a little bit limited in the sense that people typically focus on a single study population, a single small or maybe not so small, but it's a single fixed static population. They collect the verbal autopsy, they sample some of the deaths, some of the deaths to be reviewed by physicians or to collect more information, and then you get this kind of validation data sets. And then people evaluate different analysis methods, different algorithms still proposed in the literature, and then they compare, and then that's the end of the day. That concludes this study. That's particular algorithms works better for my population, and what is a fraction of the people dying of each disease in my population. Those are basically the conclusion. Okay, so this is typically how the studies are set up now. But what I want to focus in this talk are actually two, well, I want to say slightly, but really quite different questions here. Those are the questions that we keep getting from our partners in countries that are a lot of times in countries that are newly adopting the verbal autopsy. So one type of question is that we only have some on-label data. We don't have the capacity to do a validation study. We don't have anything else. We just have this verbal autopsy data. It's the questionnaires there. We collected this information. How do we analyze them? Okay. So the way that I tend to frame this is more about the generalizability of our algorithms analyzing the data. So we can always answer the question of in a well-defined population, which algorithms works better, how we should analyze the data. But then how do we design an algorithm that we know that can be robustly applied to a new population or before we even see what the data will look like. Okay, and what if that population does not have validation data sets for us to benchmark or to compare the methods? Okay. Another question that I want to mention here, just to complete this circle. So the way I see the first question is, given the limitation of the data collection, how does that inform us about designing algorithms? And the other direction is that given that we have all these insights from analyzing verbal autopsy data, can we do something better in terms of data collection? Can we go back and say that so you can collect your data in a more efficient way based on the information that we learned from working with data? Okay, so this is a question that's I don't think anyone has explicitly asked to us, but it's always hidden behind their alternative framing of the question, that they don't have enough resources to do verbal autopsy at a large scale. The interviewers complain the questionnaires are too long. They don't want to conduct this 300 questionnaire to a family who just lost a member. So are there anything that we can do about this? Okay. Yeah, so the way that I will frame this is basically that given, I'm going to put this in a little bit of a can here. That's in an ideal world, that's suppose that we have the algorithms that we know that we will analyze the data with, then can we simplify the data collection process? Can we make the data collection process easier? So that's the circle, that loop that goes back to the other direction. Okay. Yeah, so those are basically the two things. I'm going to talk about two projects related to each of those, and I will try to combine some of our thoughts towards the end and trying to bring this into a more complicated loop, entire loop that goes through the two nodes continuously. Okay, so yeah, so that's the setup. Okay, yeah, so the first thing I want to talk about is adaptivity or generalizability of the algorithms. So I guess before we get into details, I should probably put my statistician's hat and have some X and Y's here, because that's the only way that I can reason about anything. So have an X and a Y. But I want to give a little bit of introduction of how the methods currently work, and then I will talk about how we think about generalizability and what do we mean by generalizability in terms of the and how it's related to the current models people use. Okay. Right, so a little bit notation here. So I'm going to use this X to denote this data matrix that contains a symptom for each death. And the thing we want to infer is Y, which is the unknown cause of death, which I'm assuming to be a categorical variable just with a predefined cause list. Typically, C here is on the scale between 30 and 60, depending on which set of cause lists that you're interested in. Some of the studies you might be interested in only very broad cause, and then you can have imagine Y being one of the 4 or 5 large categories. Okay, then our target of inference here, what we want to get at from after collecting the data about the data matrix X is one is a cause-specific mortality fraction, or in this notation is just probability of Y. Another is individual classification, which says that given a X, how do we predict for an individual the cause of death? So the conditional probability of Y given X. Okay, so the insight that the field has been essentially built around is that here the missing piece of information is essentially just probability of X given Y, probability of symptom given cause, the tendency to have certain symptoms given each cause of death. And the idea is essentially that because the symptoms are the consequences of cause of death, if we know for people who are dying of different diseases, how likely they will have certain symptoms, then we can use Bayes' rule, can backtrack the other way around the conditional probability of the classification probability of the outcome given the X. Okay. Right. So in practice, where does this information come from? The two approaches that people have developed. One is coming from expert domain knowledge, which basically means that we're going to go to physicians and we're going to ask them, say, this kind of question: how likely for a patient die of malaria to have develop fever prior to death? Okay, and we're going to go through each pair of symptoms and causes. It's a quite challenging task. It's a lot of things to elicit. The physicians don't agree with each other a lot of times, and you'll be surprised that how often they don't agree with each other.
Are we trying to get at the proximate cause of death or underlying causes?
Yeah, it's a very good point. Yeah, so underlying cause of death, all of the things I'm going to talk about here. Yeah, there is the question of how do we get the multiple cause of death, but I don't think there's any study yet on that. Yeah, so it's something that you'll see on the last slide is on the related to some of the open questions that I think is still not addressed at this point. But yeah, everything we're talking about is underlying cause of death.
But for example, like malnutrition, it's underlying many other causes of death. So that would be one of the 30 or 60.
Right.
You would be
Exactly.
getting malnutrition.
Yeah.
Okay.
Yeah, and you can see because of having this multiple cause of death, listening this information from physician becomes more difficult. So when people think about malnutrition, you might be thinking about different things in different physicians' heads. Yeah, so getting this kind of information is really difficult. And of course, you can only look at one symptom at a time. You cannot really get at the combination of symptoms because then the potential number of combination explodes. Right. So yeah, but nevertheless, there is a lot of effort in getting the domain knowledge, especially at the early days when we don't have a lot of good reference data. So this is the only way that you can get any information that relates into those causes. Another direction is probably more familiar for people who are familiar with the statistical learning, machine learning, that you can estimate them from data. Right? So the idea is that if you have training data, you can estimate essentially anything, subject to all of the caveats of you have to have a model, the data cannot be too sparse. For rare diseases, you wouldn't have those rare diseases in your training data, and there may be label noise when you're assuming that you know the true cause of death, but they're actually not correctly specified. But essentially, if you collect enough training data, potentially you can think about estimating those quantities you need from the training data. Yeah, so it's just a schematic plot of what this look like. Yeah, so I can spend an hour talking about each of those two things because we have a big study. We have two big studies working on each of those, collecting information from physicians, dealing with their disagreements, and one collecting training data, collecting reference death data. And putting them all in the global archive. So there are a lot of specific challenges we can discuss if you want about either approaches, but at the end of the day, the main idea behind all of this endeavor, all of this effort is that we want to estimate the conditional probability of symptoms given causes through either of approaches.
I'm sorry if you said this, but the physicians you're interviewing are local.
Right, that's a very good question. So the particular project that we're doing right now, we're actually inviting physicians from a diverse background, so from different population, have different expertise.
Because it seems like the quantity is not so much the probability of having condition as the probability of somebody describing that.
Describing, reporting, yes. Yeah. So that's a very good question because that's the point I'm getting at, which is that this quantity, this probability of X given Y, is really something that's ill-defined, and it's a pretty big assumption that this is something that we can estimate and it can be applied to the model. Yeah. So hopefully some of the methods that we'll develop will get around or approximately getting around that issue, but we'll see. Okay. Yeah. All good questions. All right, so yeah, so just to put us back to the notation before, then essentially all of this is what all of this is getting at is that we want to make prediction of cause given symptoms, and then because of Bayes' rule, we don't need probability of symptom given causes. And essentially, all of the early work of verbal autopsy builds around this even more simplification assumption that the symptoms are conditionally independent given the causes. Which means that you only need to have a matrix that tells you the probability of observing one symptom given one cause, and can plug it in, do an IE-based classifier, you can classify the cause of death in that way. And if you assume all of those parameters are fixed, all of those probabilities are fixed, you get your deterministic prediction. Okay. It's very simplistic, but it has been applied in the field for a long time. Okay, so there are a lot of extensions here. You can think about incorporating uncertainty. You can think about incorporating domain knowledge of the parameters. So those are some of the work that we did when I initially was exposed to this problem. And then we can think about further developing methods that account for the dependence. We don't assume they're conditional independence. That's pretty much my PhD dissertation there. And there are a lot of other things people have developed for their specific problems that you might think about the distribution of symptoms given covariates. Right? For people of different age and sex, different subpopulation, that distribution might be different. But the fundamental problem that I want to point out here is that in all of this work, that we all assume that there is some form of this conditional probability that can be estimated and it can be transported. I can test my algorithm extensively in my population where I have validation data, and I'm confident to say that these methods can be applied in a different population. And the reason behind that confidence is essentially this assumption that this conditional probability is the same and can be transported to different populations.
Another issue seems to be that the pi sub c's, let's say you're in a population with really limited data, there isn't very vital statistics data, and you would have to know the distribution of causes of death in the whole population. So if you're in a new population or an understudied population, it feels like that may be a big lift to even know those pi sub c's.
Yeah, exactly. That's a very good question. I didn't get into details here, but here the pi of c is more of a prior guess of the population fraction, right? But in some of the work that's on this slide, essentially we're directly estimating the pi of c as we go along. So in the Bayesian framework, you can do this in the update population fraction update information individual. I can get around with that a little bit, please.
When you're thinking about transportability, are you thinking about the difference between deaths in a hospital and deaths in the community? Or are you thinking about deaths in one country and deaths in another country? Both?
So the way that I'm thinking about it is more of both. So for any two populations. So the initial, if we go back to that 2008 paper, the initial idea of estimating this symptom given cause conditional probability, the rationale was that this conditional probability is the same among the hospital deaths and among the community death, right? So that's what leads to all of this work. Yeah. But I think I accidentally scrolled forward a little bit, so you already know that I'm going to say that it's not a good assumption. Yeah.
Just the whole Bayesian framework seems to me very applicable if I want to make optimal estimates of an individual's probability. But if what I'm really interested in is the marginal distribution, and I don't care whether I get something, I don't know what fraction of the population died of HIV or something like that, then is it really appropriate to be putting in all this prior information about what fraction of the population dies of HIV? It sounds even more problematic than we usually think of Bayesian analysis would be.
Yeah, exactly. So putting in any prior information is also, to my mind, is a dangerous thing. So the work there, we're actually putting very non-confounded prior on that pi c. So we're not giving any prior information. We're estimating it a long way. So the idea is that if you start from a uniform belief of the cause of death and you get 70% of the classification being HIV, then you should probably update that pi to be more heavily on HIV. And you do this until it converges to the base. Yeah.
So you see the problem more as less the pi problem than the thing that blew up here, that the relationship between these reports and the cause, not so much whether what we do in South Africa is applicable in Morocco.
Right. So in a general case, I think when you have relatively large sample size, the problem with pi is statistically easier to solve than assuming this matrix of conditional probabilities are the same. I think, but to your point, I think we're actually working on something right now, which again is in the ongoing work size. You see that there we're thinking about estimating subpopulation specific mortality fractions, and then in there, the modeling of pi directly actually will make a lot more sense because the sample size is smaller and there's structured information, but it's a harder problem. Yeah. Okay. But in the general case, if you're just having different population, each population have a reasonable amount of samples, then I think the problem with estimating pi is easier to solve than the problem of assuming or somehow estimating the new conditional probability. Okay, and probably as a side comment here, that's, as I was saying before, that's people do this kind of validation studies, but essentially all of them is not validating on what algorithms work better. It's more about what assumptions is less violated for my population. So if I assume a particular set of conditional probabilities which happen to agree a little bit more with that population, then my algorithm is going to work better in that population. Okay. Good. Yeah, so I'm just going to quickly show you some of the empirical evidence. That's why we think this is not a very good idea. So this is probability of symptom given cause. So the probability of drinking alcohol and having trouble breathing, the two indicators, given different cause of death on the rows. And this is from a data sets that I'm going to show you with more detail later on, that where the data collected from 6 different study sites. So those are the columns. And the color indicate the probability, the conditional probability calculated empirically from deaths within that sites. Okay, so what you would expect is that across the rows, the colors should be different because they're conditional on different cause of death. But across the columns, they're the same conditional probability, but just evaluated at different population. If the assumption holds, then this conditional probability should be more similar across the population. And I guess we can all see now that the more difference is actually found across the columns. So, right, and of course, there's a lot of caveats here that I'm only looking at one symptom. So if we're plotting the symptom combination, if we're further have conditioning on sex and age, you might get different results. But the take-home message is essentially that, especially for the models where only these kind of single symptom conditional probabilities are used, this is a huge assumption to say that if I observe data from all except Dar es Salaam, and then I compute those conditional probabilities, it's the same conditional probability as I would have if I collect data at Dar. Okay.
And so these causes were evaluated in a validation study by physicians who were looking at verbal autopsy data and then making.
Yeah, so this particular data set is actually not exactly community deaths. This is hospital deaths where they conduct verbal autopsies. They do have gold standards, gold standard to whatever degree causes. All right, and just to make sure that I'm not cherry picking two symptoms that are very different, this is plotting the same. So every dot is a conditional probabilities for a symptom given a cause, and each of the panels, it's harder to read here, but each of the panels are from one site. And again, if you expect those conditional probabilities are the same across the site, then every dot should line around the diagonal in each of those side-by-side comparisons. And this is just probably showing everything there, a lot of caveats about sample size, but still you can see that the values are vastly different across different sites. Okay. Right. So essentially, this brings us to the question that essentially, how do we make use of the training data sets or potential multiple training data sets, where not only the distribution of Y is different, but also the conditional distribution of X given Y, the symptom given cause, also difference. So if neither of the two things that we can we can use, we can assume is constant, but we can assume we know how do we make prediction for a new study domain. So the few existing work after this problem, one along the direction of further conditional covariates. Another considers the using a small number of labeled data essentially to bias to further correct the inference. So if I have some validation data in my population, there are some very nice tools that this group at Hopkins has developed to correct for the inference at the population level. Okay, Yeah, so basically the goal here today, what I want to talk about on this direction is that can we, going back to the situation where someone comes to us with data sets, just unlabeled data sets, can we have a principled way to design our algorithm so that they're robust to potentially this kind of distribution change across the domains? Okay, so I'm going to go relatively lighter on the notations here, but more focused on the intuition that our big Bayesian task starts with a data generating process, and essentially our idea is that for every death there is a certain probability that is caused by cause C, and then we're going to say that within the cause C then there are different subtypes, unknown subtypes that's indexed by this latent variable Z. And then given the Z and given this latent variable, latent class and the cause of death, we're going to say that's my symptom distribution are condition independent of each other. Okay. Again, I'm not describing just yet how this corresponds to domain, to the changing distribution across different domains, but this is just the starting points where we think could potentially describe the situation that you have different distribution of symptom given causes across different places. Okay. Okay, so I'm gonna skip this notation just a bit because I think this is much easier to understand what I'm saying, which is that I'm gonna assume that the colors up there is, you can think about those as symptom patterns, the symptoms across the rows. And so the first group come from the first cause of death, the second group come from the second cause of death. And there is some kind of baseline symptom profile, and we allow that within people who die of the first cause of death, for example, there are different profiles of their symptoms, but we don't know the exact makeup of those different profiles. We're going to estimate that from our data. And just to make our methods more robust to this messy data, we're going to try to say that we want the different symptom profiles to borrow information from each other. We don't want to estimate all noisy profiles. There's some baseline, they're only deviating from the baseline in some of the coordinates.
Just a question on the last bullet, is that related to sort of reporting error? Is that just saying that the probability to report a certain symptom conditional on cause of death is independent of reporting others? Does that account for people who are just like bad respondents, who don't remember stuff?
So, yeah, very good question. Right, so everything we're showing here, because X is reported symptoms, so every conditional probability is probably of reporting that symptom. But we're assuming that they're condition independent, given we know which latent stratification they come from.
So is the intuition here that you like fix the cause of death and then there's different clusters of symptoms that can happen?
Exactly. Yeah.
Could you repeat that?
There are different clusters of death within the same umbrella of the single cause of death.
The different clusters of death within?
Different types of cause of death within a certain cause of death.
Oh, so there's not one pattern that is cause of death. There's multiple
There are multiple
patterns, and
patterns.
individuals fall
Fall
into
into
different cases.
Yeah. So probably it's already clear why I'm getting at this kind of representation, because essentially go directly to the schematic. Essentially, the idea is that with enough patterns within each cause of death, then we can think about the difference between different domains, being that different domains have different mixture distributions of those latent patterns, right? And then yeah, and some of the patterns may make macro sense. Some of the patterns may be just patterns of reporting. Essentially, it's going back to the idea. You may have a pattern that's the same, almost the same as a different pattern, but they more likely to report, say, drinking behavior. Those will be considered as two latent classes in this kind of framework. Okay, and we're gonna basically, then this means that for all of domain prediction, essentially, if we keep this part fixed, then we only need to estimate for a new domain what fraction of people will fall into each of the patterns. We have a little bit more deeper freedom to decide or to classify people into different groups. We're not only classifying them into cause of death, we're also classifying them into specific patterns, specific subclasses. Okay. And in this paper I'm talking about, we actually make a very simplified assumption at the end, which says that's the prediction, the domain is going to be just a weighted average of the existing ones. Okay. There are a lot of things that we're exploring right now to make that a little bit more useful in practice, but this is a starting point. Okay, so let me quickly show you some of the results. This is from the PHMRC gold standard data set I was showing you earlier. There are 34 cause of deaths, 168 binary indicators. Study comes from 6 different study sites. And I'm gonna skip some of the details here. But essentially the result we find, of course, if I'm presenting this, the classification accuracy for all of domain prediction. So we'll leave out one side, use 5 sides to train a model. It outperform existing models by a lot. And one of the things, the thing I really want to show is actually here, where again, this is each panel is predicting on one domain. And this orange line corresponds to the state-of-art methods people use in the fields. And this purple line corresponds to this new approach. So those are all assuming that you don't have any validation data to further calibrate. And then we can, if we assume that we have some small number of data from the target domain that we can use to calibrate, that becomes those box plots depending on the subsampled calibration sets. So for all of those methods, the prediction accuracy would improve. But what we see here is that in probably all except star, that's even without those additional calibration data, this new method outperformed the current methods with the calibration, with additional data set to calibrate. Okay, so that's pretty promising results that we initially were experimenting on. Okay, so yeah. Okay, so I'll probably go very quickly on some of the results, but one of the other things as we go through this is that we can interpret the intermediate results, the model parameters, that this is some of the symptom profiles, that's green and blue panels from before, and we can see exactly how those different profiles are, and we can interpret whether or not it makes sense in practice, because it's on a scale that everyone can understand, just conditional probabilities. Some of the causes you need more latent classes to capture. Some of the causes like drawing is pretty much straightforward. You don't really need that many degree of freedom to characterize. Okay, as we look at the distribution of different latent classes across different sites, and we can see, for example, how the sites are related to each other when you're making prediction for, in this case, Pemba Islands. Which part of information, which part of those 5 sites are you using more? And in this case, the information is more using the from DAR, which makes sense. It's the same country.
Yeah, some of it seems like, given you have more flexibility with the different profiles, it makes sense that you would fit better. Mm-hmm. But is there a kind of downside of that fit? Is there some overfitting concern, or like, you know, in terms of inference, is there a downside to that flex? I'm just trying to understand why not just have an infinite number of profiles.
Right. Yeah.
Like at what point do you hit the downside?
Yeah. So in this particular data sets, we actually find that with 2, 3, 4 latent classes, it gives us overall the best performance in terms of the cross-validation accuracy. But as you have, exactly as you said, as you have more latent classes, you are more likely to overfit. They will capture something that starts to not make much sense anymore. But I imagine that's something that depends on the particular data sets that we use. We're kind of limited by the fact that this is the only kind of open access benchmarking data set everyone uses. So yeah, that's what we're finding is. Okay. All right. Yeah, so let me wrap this up fairly quickly, and I will show you probably one figure from the other direction. of the cycle. Yeah, so we're, as I said, we're expanding our work on this. Instead of multiple sites and predicting new sites, we're thinking about a few different extensions, especially when you have different subpopulations and you have data that are collected of subject to some selection bias due to different stratifications in your population. We're extending this access to those kind of within population adaptivity as well. Yeah, so I'll come back to probably to that towards the end, but let me just very briefly talk about this work of doing this adaptive questionnaire. I think this is really something that's whenever I talk to people about verbal autopsy with all of the limitations, there's always a question of why do you still use verbal autopsy? It seems that it's just a very messy tool. Yeah, there's a natural limitation, which essentially leads us to think about can we reimagine this whole process of data collection, this whole process of going through the questionnaire, collect all the information we have. Right, and I guess another point here is that for most of the statisticians, we're familiar with the regime where, given the data have been collected, we develop something for that data. But we were, at least for a lot of us, we really think about how does that change our recommendation of how the data should be collected. And as I said earlier, asking this many questions is just going to create a lot of emotional burden, and it's going to take an interviewer an afternoon to do one interview, and it becomes it becomes a costly thing, a lot of the low resource settings. Okay, so so I should also say that there are a lot of efforts to try to cut down the number of questions, but then there's always a balance that if your questionnaire is too short, then you don't collect enough information. So what seems to me the real opportunity there is that the questionnaire should really be individualized, meaning that for some of the deaths, you don't need to go through all of the questions. For some of the deaths, you do really need to collect more information. So the idea is basically that if we can definitely choose the next question based on the information we already collect, and if we can choose, if we can stop early, for example, and then potentially we can solve this problem of asking this many questions in a very costly fashion. Okay. And for any of the students in this room who have taken GRE tests, you have been subject to the similar type of ideas. So there's been a lot of work that I've been doing in the machine learning literature, in the computerized adaptive testing literature, where you answer the question that changes the next question you get. And more recently in an online survey. And essentially the idea is that, just gonna go to the key points here, that's if you can pick the question that gives you the most information on each iteration, then potentially you can stop early once you're confident enough that you have collected all the information you need for the classification problem. Okay, so I'm gonna skip all of the mathematical details. There are many different ways of framing this. We basically went with one simple approach that looks at the KL distance of the questions. We made it a fully Bayesian score where we actually incorporate into our optimization problem the uncertainty we get by fitting the model on the sets. But let me just go directly to the main results here. This is the same data set, the same PHMRC data sets. And the two green and the blue lines there correspond to two different active strategy. And this is assuming that, say, if for everyone we just ask questions, we just ask the first 50 questions, then the black line corresponds to the accuracy that you get by collecting the 50 questions from the questionnaire. And those two correspond to two different versions of this adaptive questionnaire design. So the stunning fact is that out of these 168 questions, basically, even if you just don't do individualized, just for everyone, just stop at around 30 or 40 questions. If you ask the right 30 or 40 first questions, you can get pretty high accuracy, and actually even higher accuracy than asking all of the questions, because the model we use to fit this data is actually a little bit misspecified, and you collect more information, collect more noise, it actually downgrades the prediction performance.
What if you asked this first question, what was the cause of death?
Right, but then most likely you wouldn't get an answer. Because
I don't know.
Yeah.
Well, what happens?
Yeah,
Certainly,
so-
last here, everybody has a theory, I mean, it'll be right, but
Yeah.
say car accident, I would say old age, I would say
Mhm.
people in these contexts don't say anything.
Right, so the questionnaire have some questions that are similar in that fashion. They're say whether or not there was a traffic accident, and that's a pretty straightforward answer. Whether or not there is hospital diagnosis of say HIV or hospital diagnosis of heart attack, stroke. Right, so I think some of the benefit we get from this is essentially that's when we ask those questions early, we're pretty confident. We'll probably ask a few more questions to practice, and when we're confident, we stop. Yeah, but in practice, it seems that those questions don't get a lot of responses.
If you ask in these contexts, what did so-and-so die of? They say, I don't know.
Right, yeah. Yes, I mean, it's not on the survey, so we don't have official data to know exactly what is the fraction of people reporting that. But based on our conversation with the interviewers, sometimes they will have some theory, something related to the stomach, something related to the lung, but you wouldn't be able to pinpoint to a particular cause of death.
But that's basically what this approach is doing. It tries to narrow in on the kind of broad candidate set of things, and then it hones in.
Right. It
And
can be
the
said
adaptive
on
one.
sentences.
And this must be assuming that you have a set of full questionnaires that. Do you have does this start from a situation where you have a lot of questionnaires for which all the questions are available? And then you can, at that point, you can start to.
Yes. Yeah. So this is assuming that we can feed our model. We can pick whatever model we want. So we fit on some data sets. We assume that we have confidence in this model, or we assume that we're gonna analyze our data with this model anyway, and then we're gonna take this to a new person and new respondents, and we're gonna see whether or not we can change it on it. That's good point. All right. Yeah. So one other thing I want to show here, because I think this is also a little bit, this is also informative in some way, is that, of course, we're talking about individualized, we're talking about different stopping rule, right? So of course you want to stop, you are confident, and you want to keep asking, you're not confident about classification. So what this shows is different panel is the accuracy of classifying death, given the true cause of death is those causes. And the color, the points don't really matter much. There are different thresholds of stopping. But what we find is that by even applying some very simple stopping rule, that's for those causes where we have a high accuracy, like here and here, is the approach will more likely to end early. So I don't know, for some reason I don't have the x-axis here, but only a small number of questions is asked. But for some of the causes where, again, this is a very simplistic model, so you see some of the classification accuracy are very low. And in those cases, we actually went ahead and asking essentially all of those questions. Which is a nice conservative thing to do in practice, I think. And just by the way, so the dotted lines correspond to, again, the state of art algorithms used in the past. So we're not getting this low accuracy because we're using terrible algorithms. We're getting this low accuracy because all of the algorithms are terrible for this figure cost.
We're kind of low on time. We're low on time.
Yeah, sure.
Sorry.
Yeah, so I think that's all. Essentially all I want to say about the particular these two projects. So I guess the final thought here is essentially that's I think the limitation of the data collection should inform our data analysis, and in return our data analysis potentially can help us with more intelligent data collection. And I think the answer to the two questions that our current thinking is essentially what we have already discussed as we go along, that we should use algorithms that are robust to domain shifts. And on average, we could potentially expect that only a small number of indicators is really useful in the surveys we collect. But we cannot just cut the questions for everyone cut down to the same small set of the questions. We have to do this in a more model-assisted way. And I think that's probably a good trade-off in practice. Right, so I'm gonna skip some of the open questions, but in all of the nice things I said, there are also the not so nice counterparts where problems can happen, the data and domain knowledge can conflict with each other. How do we characterize the domain relationship with each other, population relationship with each other? And once we collect the data using this active questionnaire, how can we actually do inference using this adaptively collected data? I think it's still even statistical place is something that people haven't thought too much about in general. And we're also thinking about extending some of this framework to essentially pick so going back to the very first question, pick the samples that are useful for us to label, to verify, so that we can improve our hypothesis. Okay, yeah, so with that, those are the collaborators. So Toshia is a student who worked on the active questionnaire in the second project, and the first one is project working with Jinke, Irina, and Sam Clark, yeah, from a few different institutes. And the two papers are there if you want to take a look. Yeah, thank you so much for all of that.
We've had a lot of questions from the room. Is there anything from chat? I think we haven't asked a question yet. Will, so we'll.
We don't have any questions on that right now. Oh, sorry, no, it's a comment. I'll share it with you later.
So just getting back to the question about underlying causes and multiple causes of death. So this was all predicated on predicting the cause with the highest probability, essentially. And you didn't say exactly how you're sort of classifying accuracy, but there are lots of different ways of sort of classifying accuracy. Many causes have multiple underlying causes. There's not a single underlying cause. And you started this off by talking about, well, if you're going to be planning health interventions, you need to have data on cause of death. Well, you actually need data on multiple causes of death when there are. So I'm wondering what's being done to try to look at where there could be multiple causes with relatively high probabilities, and they may actually have overlying prediction probabilities too.
Yeah,
what's being done on that?
Yeah, so unfortunately, almost nothing at this point, because I don't think there's any data sets where the multiple causes actually exist. Well, I think now that probably changed after COVID, because there is more data collection during the COVID periods that actually might contribute to that. But essentially, for my personal thinking, the way that I'm representing different underlying cause of death as coming from having different symptom profiles, essentially my intuition is that those symptom profiles can give you a sense of different I guess multiple causes of death assignments. But right now I don't have any good data on essentially how you can interpret that, so you can make sure that's something interpretable, but that's potentially something we can even compare across different causes. If there are certain symptoms similar symptom profiles underlying different causes of death, then maybe what it says is that there are multiple causes of death, and for those two groups that share the same second, third cause of death.
And with your data, you could get a predicted probability of lots of causes of death, and you could actually see where there's some clustering.
Exactly.
Is it the case that it's much easier to predict young deaths than old deaths? I mean, kind of consistent with this idea that there are multiple causes of old deaths and a single cause of young deaths. Is that an empirical pattern that you find?
Not consistently. In some population, yes. Right. In some population, so it really depends a lot on the population. If there is a very high HIV prevalence, then some of the younger deaths are actually easier to classify. Sorry, I guess that's the example that's along your direction. But there are situations where the younger deaths are difficult to classify, but the older deaths are easier. as well.
Yeah, I was curious, you mentioned COVID, and I was just thinking about how do you think about generalizing this in settings where, again, there may be some pandemic or something else that's dramatically shifting the underlying relationship between symptoms?
Yeah, so it's a very good question. That's essentially Zoe's dissertation project right now. Yeah. So the idea is basically when you have a dramatically changing pandemic, then all of those conditional probabilities change dramatically over time as well, and potentially over different cohort. Should I use that word casually here in this department? Different subpopulations. Yeah, so what we find in COVID is that the probability change a lot by age over time, and then potentially also depend on the vaccine status. Right, so we can think about the whole population as this shifting subpopulation over time, but we're still formulating exactly how that can be more generally used for surveillance purpose. The problem with there is that essentially you get into smaller sample size as you look at finer and finer stratifications.
Okay, we are out of time, and thank you so much for that really fascinating talk, Richard.
Yeah, thank you so much.
So much, that was really